Hello, this is Jack Jackson. We're continuing our 8th playlist here in Calculus. So I'm going to label these videos as, Calculus 8 point something. It's my 8th unit or 8th playlist in Calculus, but it's actually the first unit in my Calculus 2 class. Okay, so continuing on here, we're going to talk about further techniques of integration. And as I said in an earlier video in this playlist, be sure that you study the playlist on playlist 5 of calculus, because that really goes through a lot of the stuff that we're doing, just reviewing here. So I'll have a couple of review videos real quickly, but there's more in depth in that playlist. So this video is going to be talking about using technology to check integrals and antiderivatives, or even to find them. So a TI-83 or TI-84 can be used to check antiderivative and definite integral problems, actually without actually showing you the answer. So to use a TI-84 to check a definite integral, let's look at some examples. So exercise 1, find the exact and approximate values for the following definite integral, and then use a TI-84 to check your answer. So I started with a fairly easy one, the integral from 1 to 3 of the cube root of x dx. Since it's a definite integral, to do the exact value, we want to apply the fundamental theorem of calculus to find that exact value. And so to do this, we must first check to see that the integrand, the cube root of x thing, the function we're integrating, has to be continuous over the closed interval defined by these limits here. So in this case, the closed interval from 1 to 3. If it is, then we can apply the fundamental theorem calculus, that is, find an antiderivative, evaluate the endpoints, and subtract. And that will give us a definite integral, exactly. Of course, then we can plug in a calculator or something to get an approximate answer if we need to as well. If it's not continuous on that interval, then we talked in the earlier notes about some things we could do with it. Okay, so in this case, the cube root of x is actually continuous for all real numbers, so certainly it's continuous over this interval, so we can go on. So we rewrite that cube root of x as x to the 1/3 power, and then we're to see it was just a power rule function, simple power function. So we add 1 to the power. 1/3 plus 1 is 1/3 plus 3/3, which is 4/3. Then we divide by the new power, in other words, multiply by the reciprocal of that power, which puts a 3/4 out front, and that's an antiderivative. All antiderivatives are just this plus or minus some constant. And then we want to evaluate from 1 to 3, which means we take this function, plug in the 3, plug in the 1, subtract. I'm going to rewrite it more like the original notation. 4/3 is 1 and 1/3. In fact, that's kind of how we got it, 1 plus a third. And so that's the 1 power is the x to the first, and the 1/3 power is the cube root of x. So we could rewrite that part like that. I'm going to bring the 3/4 out front of the evaluation here. So I just take the x times the cube root of x, plug in a 3, minus x times the cube root of x, plug in a 1 for x, add those together, actually subtract them, and then multiply that 3 by that 3/4 out the front. Cube root of 1 is 1 times 1 is 1, so we got a minus 1 there. And so the correct answer for the final answer for an exact answer is 3/4 times parentheses 3 times the cube root of 3 minus 1. If we type that in a calculator like I did over here, we get this decimal approximation here, 2.495061533, as far as that calculator will go. And in fact, we can check that by doing on a TI-84, we could do math 9, and it will get this symbol here. There'll be little boxes where the 1 and the 3 and where this is and where the x is. You put the lower limit here, the upper limit here, put the function formula here, which I wrote as in the fraction exponent form. I think there actually is a way on 84 to get a cube root as well if you want to do it that way. And then I put in the variable here, which is x. And it does basically does a version of Simpson's rule or some type of numerical integration technique to find that answer, which is we see is just as good as the way we did it before as far as that many decimal places. So it checks. If you have an older T83 or an older operating system on the 84 or the T84 with the math print turned off, put it in classic mode, then when you do Math 9, instead of looking like the regular integral notation, it'll say FNINT, open parentheses. What you do is put in the formula, comma, the variable x, that's like the dx, then comma, lower limit, comma, upper limit. So notice you still have 4 inputs just like you do here. It's just in the newer operating system, it's better because it actually looks like we actually write it. But either way, it's going to give you the same number, and you see that it does check. The approximate values do check. Now that's going to be for a definite integral. Definite integral, of course, is a number for an answer. What about checking an antiderivative? Well, we can check any antiderivative problem on a TI-84 as well. Okay. And we take the derivative of the resulting answer by checking that we obtain the original integram function. In other words, you want to check a antiderivative problem by taking the derivative of the answer, and we get the original. So let's just do the family of antiderivatives here of 5x to the 8th dx. Okay, or we might call that the indefinite integral. Well, it's pretty easy again. You just let the power go up by 1 to 9, multiply by the reciprocal of that power, which is 1/9 times the 5 is 5/9. It's a whole family of antiderivatives, so we have the plus c. And of course, the reason why we know that works is because we can take the derivative of the answer and we should get the original back. The derivative of c is 0, so that part always goes away. And then we use the power rule. 9 times the 5/9 is 5, and the power goes down 1 to 8. So we do get the 5x to the 8th. Basically, we could reproduce this check on the calculator. What we do is we put the thing that we're trying to take the derivative of, which is our answer, 5/9 x plus 9, x to the 9th power, excuse me, and then you can put plus whatever c you want. You can actually put plus c, and it'll just use whatever's stored in c, or you can put plus whatever. You might as well just leave it off. Just use a 0 there. And we'll see if that checks. Well, what you do in y2 is you put the derivative of y1, the numerical derivative, and then in y3 you put the original function, 5x to the 8th, and if this is done right, the tables for y2 and y3 will match as you see the check over here on the right. Now, how do you get this line for y2? It's math 8, okay? So we do that. Let me maybe go ahead and type that in here. Use math 8 to get the numerical derivative in y2 on a TI-84, 83. This looks like numerical derivative of y1 with respect to x, evaluated x. And on the older operating system, you have an option of putting in the an h here, smaller h. It defaults to h equals 0.001. Okay. So anyway, that's how you can check them. Check any derivative problem by putting the original here and your answer in original in y1, your answer in y3. Make sure y2 and y3 match. Check any antiderivative problem by putting your answer in the first one, y1, and the original problem in y3, and y2 and y3 should match. So, this is important. If you are allowed TI-84 level technology and have it available, then you should never have an incorrect answer to an integration problem, at least not without knowing it's incorrect. However, this level of technology does not actually tell you the answer. On the other hand, a computer, phone, calculator with a computer algebra system, CAS, will compute the correct answer for you. For example, the TI-nspire CAS can compute most antiderivatives and find exact values for most integrals. So let's see how that works. So some calculators and computer programs can find exact values of definite integrals and antiderivatives. Like I said, the TI-nspire CAS is one such calculator. Notice it does not return the plus c, so you have to put that in there yourself when you're trying to find a family of antiderivative, or in other words, indefinite integral problems. So, for example, if we want to find the exact value of the integral from 0 to 3 of square root of x dx, we just type that in here, and it'll do an exact value. If you want it approximately, you do, there's a way to get the approximate there by just doing approximate equals. Let me just show that to you here. So we have a calculator here. Let me just clear some stuff here. Okay, starting with a clean calculator. This is the screen. Well, let me just do it. Let me just show you like this. So there's what the calculator looks like. Okay, and this is a CAS version, or at least an emulator for that. Now, the way you get that on the TI-nspires is you go to this little menu thing right here, and you click on that, and you have templates here. There's some up here for derivatives and fractions and square roots and different things. Here's the one right there for definite integral, and here's the one for indefinite integral or antiderivative. So I'm going to go to the definite integral one and click on that. You can use your arrow keys to help you with that. And now we just have a template to fill in, so it's pretty easy. Just 0 there, 3 for the top. Our function is square root, which is there, of x, and the variable is x, and enter, and it does that. If I have that same thing, but I hit Control and then Enter, it'll give me an approximation. And I can make the calculator by going to Mode, show me some more digits if I don't, if I want that. So, for example, I can go to Home and go to number 5 to Settings, and I can go, I think it's under Handheld Setups. No, it's under Document Setup. 5, Document Settings, and I can tell it to do, this one will go up to like 12 significant digits. So I just tell it to go to 12 digits. You, of course, use radians for sure for calculus. So now if I just take this and approximate it, I'll get even more digits. That's as many as it'll show. So anyway, we can get exact values and approximate values there. Now, if I want to find the antiderivative, then I go to here and click on the antiderivative button, right? The family of antiderivatives, the integral sign without limits, and I can plug in the function I want to find an antiderivative of, and it will tell me there it's 2x squared over 3. Sorry, 2x to the 3 halves. Okay, so that's how we got that. Now, there are many other things and other programs and things that will compute antiderivatives, formulas, and definite integrals exactly, things that have CASs built into them, computer algebra system. And GeoGebra is one such program. It has a CAS built in. And I've used it to create a GeoGebra activity that allows the user to enter the integram formula. And the app can then calculate an antiderivative and or a definite integral and then illustrates these graphically. So if you click on this, it will take you to my app. Actually, I think I already have it open. Let's see. Yeah, here it is here. And I have here's the app. And notice you just type in the formula right here. And if you click this button, let's just put an easy one in there. X squared. There it is. if I click antiderivative, it'll show me the formula, 1/3 x cubed plus a constant. That constant starts out at 0. Actually, let me show you. You can actually go over here to Algebra, find C5 right there, and by changing this, I can get different antiderivatives, but they're all just shifts of each other. So I'm changing that value of C5. Okay, but most of the time you're not going to need that. You just need to see one of them. So I'm just going to leave it like that. We can just click here and move around. We can zoom in and zoom out by using the scroll on your mouse. So in any event, there's a there we see the antiderivative, at least one of them. I can also do a definite integral by, say, going from, say, 0 to 1. Let's say from negative, let's do it this way, from negative 0.5 to 1, and it will do that area. Let's see if I say minus 0.5. So now it's the green area minus the red area is the integral. And notice it actually did it exactly. Negative 3/8 in fraction form, or negative 0.375. So it will come up with an exact value. At least if you can put exact numbers in here, it should come up with an exact value here and an approximation in decimal form, as well as looking at an antiderivative. Okay? So that's a nice little thing, and it gives you a nice visual, pretty easy to use. That's a free GeoGebra they've made available for free, and I have this available for you to use. Let's see, I think I already said everything that was there. So here's an example that you could try yourself. Take the integral of sine of x dx from -1 to 3. Use the app to go ahead and see if you can reproduce what you see here. Here's the integral from sine x from -1 to 3. The exact area is this green area minus the red one. That number is the answer, which is exactly cosine of 1 minus cosine of 3, or approximately 1.53029480032. Lots of digits there. An antiderivative for sine of x, which would be basically the answer to the second one, is negative cosine of x plus an arbitrary constant. Now it's graphed that with the constant being 0, but again, you can get in there and change the constant as I showed you just a minute ago if you want to see a different one, which is just all it's going to do is take this green graph and vertically shift it. All right, so going forward, be sure that you can work all the integration problems like the ones in these notes and the notes from Unit 5 entirely without the aid of technology. So only after working them by hand should you use technology to check your work. However, remember that the focus needs to be on doing these without technology, at least for the purposes of what I'm doing right now in my class, because among other things, your exam will be a no technology exam. However, if you do have technology available, then it's a very good idea to check your work. And although some of these integral problems are relatively easy, others can have many steps, giving many places to make some small error. So be sure to use technology to check your work when you can. Throughout these notes and in these playlists here, there will be some technology check provided for, well, probably all the exercises, or at least most of them. All right, so now that we know a little bit about technology, we can use that as we go forward. We'll start looking at some more integrals in the next video.